mentioned a little bit of my experience with MAM conferences. So I think my first one probably was at Pisa, and I count myself as one of the lucky ones who actually met Marcel Nutz in 2011 in New York. Not only met, but also interacted with him and became Facebook friends as well. So I got really impressed with him as a researcher, mathematician, but also as a human being with his ethics. Really, really wonderful person. So really happy to be again at another MAM conference, and I hope we'll have many more to come, and I hope I'll be able to come to another one in the future or more. So my talk is in some sense continuation from what Barbara already introduced you to, the methodology that we've used to analyze cyclic stochastic fluid models. That collaboration was inspired by some applications that I worked on. So I have a couple of examples here of some plots. So one is from healthcare, modeling patient flow, and one is from modeling El Nino climate, and I hope you can guess which one is which, maybe. So the one that has healthcare, you will notice a particular strange behavior anomaly there. And if you recall, a few years ago, that something happened, and that might explain the dip there. I, in fact, applied stochastic fluid models, not cyclic ones, but just fluid models, to the analysis of El Nino with an honor student. And so there's definitely application potential to many real-world phenomena where we have seasonal behavior, right? Cyclic behavior where the cycle might not be constant or might not be constant, might have some distribution. Also, there could be some other, some trend of how things grow, and so the behavior might be a lot more complex that maybe we consider in the sort of initial model here. But the general idea is that you have some cycle, some seasonal behavior, and we'd like to be able to model real world systems to be able to understand them. Because of course you can simulate things and you can apply some numerical methods, machine learning and so on. But I'm really interested in understanding the behavior, the dynamics of the problem. And so if we can develop some model and understand how this model behaves, that's something useful and interesting. So that's what I'd like to do. And I had a chance to meet Barbara at one of MAM conferences, and we started talking, and I got really interested in her work on cyclic QBDs. And so that sort of sparked the conversation, and that's where we are now. So what's the idea? Cyclic stochastic fluid model, which is an extension of the standard fluid model. The idea is that you have a level variable which models some continuous measure, some continuous metric of some process. So could be amount of fluid in a telecommunication buffer, level in a water reservoir, or amount of data, or if we count customers as fluid, and phase could be some underlying environment that drives the evolution of this process. And so suppose that the generator is such that there is some constant cycle without loss of generality. We're going to assume that that's just one, because you can then rescale things. Note that here we assume that the rates are constant, but in fact in our earlier paper with Barbara, we sort of did mapping, so it's possible to make them time varying as well and then map to constant rates model. So the level evolves in a way that its rate of change depends on this underlying environment. So so if you would like to visualize this, the behavior may look somewhat like that. So this is an example of some simulation of an example from our earlier paper. Okay. I'm going to use this example to illustrate some results. So here we have 3 phases with positive rates, 1 with 1 and 2, so these 2 with negative rates and 1 with 0 rate. And the generator, as you can see, has cyclic behavior. There's sign function here. One matrix that is useful in some calculations is the standard psi matrix, but in a slightly different context, because now we have cyclic behavior. So that's to do with distribution of busy period, or if you like, if the process starts from some level going up, it's about distribution of when it hits that level again at some time in the future. So we're interested in that matrix. There is psi st, and then there is hat psi st, which is the sum of all psi st plus n. So the meaning of those is that psi st is this the distribution of busy period, assuming you start at time s in some phase and hit that original level at some time t and do so in some phase j, while the hat function, the idea is that when you start at s, you hit the original level at some time in the future, at some time t plus n. So basically, you're saying at time t within this cycle, right? So we sort of think of time now being positioned within this cycle in our analysis, right? In our earlier paper, we derived some algorithms, some expressions for this psi matrix. So, this is just application of these algorithms, and this is like sanity check. Do things look okay? So we look at row sums. Okay, they look the error is pretty small, so we're sort of happy with the results. Another matrix that I'd like to mention is U0 and U hat 0. So U0 is to do where you start at time s at some level, and you don't change the level. So the process in one of those phases with 0 rates, right? So, and then U hat 0 is that function where you say you start at s and you are until some time t within the cycle, or t plus n if you think about actual time, observed time. So if you take sum over all n, you get your U hat 0 function. So the idea is start at s at some level, and you do not change the level, so you spend that time in those phases with 0 rates. And we also have fluid generator, where I borrowed the idea from my earlier idea developed for the analysis of fluid models. So it's convenient to think in terms of rates of change with respect to level rather than time, because then this leads to some convenient expressions for example, for the psi matrix and analysis of the fluid model. We assume that the drift is, so the average drift is negative to ensure the stability. And I guess like if you think of the meaning of that, if you pretend that the time is part of the state space, then it kind of makes sense that we would like to have this negative to have stability condition. So often, in order to understand some expressions, I sort of think in terms of T. Just pretend for a moment that T is part of the state space, and it's kind of easier to believe some of these results. Gamma T is this limiting asymptotic periodic distribution. You will see it some slide later on, defined like so. And we are interested in limiting distributions. So introduce notation for those. So we take limits as n tends to infinity. So effectively, you look at T being at some point within the cycle, right? And you ask, what is this limiting distribution at that point? Then we have differential equations, and applying this method that Barbara has so well explained in her talk, the idea is to develop expressions for the Laplace transforms so that we can evaluate this limiting distribution. So here is the key result, connecting the limiting distribution and corresponding Laplace-Stieltjes transform. Now we assume that the process is in asymptotic periodic equilibrium distribution, so that we assume that at any time point T within the cycle, the equilibrium has been reached. And then we have this result for the Laplace-Stieltjes transform. And you can see that it involves the quantity which we denote as W tilde, which has interesting interpretation as the one-step transition probability matrix when you move from time T to T plus one. So sort of one step in a discrete sort of process evolution. Because you can see this interpretation from this equations, right? I'd like to mention interesting connection with the constant rate fluid, because then you will see something interesting also emerging in terms of physical interpretation of this matrix. So let's consider the hat function, which just as before, you take sum over all k, so you take t plus k. So effectively, you think in terms of those hat functions sort of correspond to some observation at time t within the cycle, right? Because if you add over all k, t plus k, you're sort of saying I'm at t time within the cycle, where t is between 0 and 1. Then what happens if you consider the constant case? So the generator is just constant, like in a standard fluid model. And then you integrate over the cycle, then you get this. And we sort of understand the meaning of that. So, so this t minus lambda c effectively is a generator that tracks the shift in the fluid, because c is the rate at which the fluid shifts, and t minus lambda c is basically the generator. And I've seen sort of similar generators in my sort of earlier work, so one on two-dimensional fluid models or some reward generator for fluid. So kind of similar idea. So it's interesting to actually see this popping in here because it gives you some insight about what is the meaning of the W hat tilde quantity. And then a familiar expression, using the method described by Barbara earlier on, we write this Laplace transform in this form. And then we're able to solve it. And also a little table with which connects constant rate fluid versus cyclic, and you can see some similarities here. Okay, we're interested in the density of the process being at, so assume that you observe the process at time t and you ask what's the density at x. So let's define that. And again, t is in the sense of being within the cycle. So t is time point within the cycle between 0 and 1. So that's how we define that. So you can see the correspondence to that position t within the cycle. And also we're interested in probability of observing level 0 at time t. Again, t is in the sense of being positioned within the cycle between 0 and 1. There are also some matrix-analytic type of expressions here that we wrote and then compared the results obtained using Laplace transform versus then comparing whether these are satisfied for our example and other examples as well, which makes sense because if you look at, for example, this one, you can think of this as a rate of leaving level 0 at time t, and that should be equal to that, and it is. So if you evaluate these quantities using Laplace transform and then compare these expressions, they match as they should. Or for example, expression for being at time t in one of the phases with 0 rates, you will see sort of similar expression that we see for standard fluid models, just in a cyclic sort of environment. So very similar expressions. Also here, if you take the, let's say on the right-hand side, if you take the pi plus c plus, that's the rate of leaving level 0 times psi, so you hit level 0 again. So if you integrate over all SNT and some over all phases, this is equal to this total rate of hitting level 0. However, at individual time points, they don't actually necessarily match, which makes sense because if you look at psi matrix, if you leave level 0 at some time s, then t, so the first hitting time t can happen anywhere between the cycle 0, 1. That's why it's useful to think of t as part of kind of the state space. It's easier to understand why that would be the case. Okay. And so this is the algorithm summary that we applied. So we first solve for gamma t, find the zeros of this matrix, then solve for pt0, and then find the k constant, then solve these equations. So this and then finally evaluate the cumulative distribution and the densities. And there's some output here for this example that I mentioned earlier on, for the different phases, asymptotic periodic distribution. So you can see there's some sort of cyclic behavior going on. And also asymptotic periodic distribution of observing various phases at various time points within the cycle. So you can see some cyclic behavior going on. Drift at time t. Probability of observing level 0, again, some cyclic behavior. All these are sort of preliminary results. We have looked at several different examples. I picked this one for this talk. For each of these examples, we evaluated the distribution, and then we also compared the output against the simulations, just to see, I guess that's a little bit of sanity check. And you can see there is a really good match here. So for different phases, simulation versus computation using the theory. So pretty good match. So this is preliminary work, but we'll submit full results later this year to PEVA. And of course, I'm interested in applications further to the various problems that I've worked on, and also related models, because there's so many relationships between QBDs, fluids, mapping from one to another, one-dimensional, two-dimensional. So there's lots of opportunities, including Markovian binary trees, that some of the results I developed use QBDs. So there's definitely lots of potential for applications. Thank you.